quantum computers. I mean, they're incredible. They promise to solve problems that are basically impossible for even our most powerful supercomputers today. We're talking about designing revolutionary new medicines, cracking encryption that's currently unbreakable. But all that power, it comes with a huge secret vulnerability, a fundamental weakness that could stop this entire revolution in its tracks. So, how do we fix that?
And that really brings us to the heart of this entire explainer. When you've built a machine that is, for all intents and purposes, a computational genius, but it's so ridiculously sensitive that a stray vibration or a tiny little change in temperature can ruin everything, how do you protect it? How do you shield that genius from its own built-in fragility?
You see, it really all boils down to this contrast right here. On one hand, you have the promise, the power to tackle some of humanity's biggest, gnarliest challenges. But on the other hand, you've got the peril. The very quantum states that give these machines their magic are unbelievably delicate. Their calculations are just constantly being shredded by errors.
And this gets us to the core of the problem, what we can call the quantum conundrum. And to really get it, you need to meet the main villain of our story, something scientists call quantum noise.
So what in the world is quantum noise and decoherence? Well, here's an analogy. Imagine trying to hear a tiny, faint whisper while you're standing in the middle of a hurricane. That's pretty much what a quantum computer is up against. The whisper, that's the precious information held in its quantum bits, or qubits. And the hurricane, that's, well, everything else. Tiny changes in temperature, magnetic fields, even cosmic rays zipping through. This constant barrage of environmental interference just wrecks the system and destroys the data.
But, okay, don't despair. Scientists and engineers are not just sitting around letting this happen. They have a plan. They have a hero for our story designed specifically to fight back against all that noise. And its name is quantum error correction.
You know, the ultimate mission here isn't to build a perfect quantum computer. That might actually be impossible. No, the real goal is to build a fault-tolerant one, a system that can do its job and get the right answer even while it's being bombarded by errors. A system that can basically weather that hurricane. So how's this supposed to work, at least in theory? It's a pretty brilliant three-step dance. First, you encode. Instead of putting one piece of data on one fragile qubit, you smear it out across a whole bunch of physical qubits. You're building in redundancy. Second, you detect. You use other helper qubits to constantly check the system for common errors, like a bit flipping from a 0 to a 1. But here's the clever part. They do it without actually looking at and destroying the core information. And finally, you correct. As soon as an error is spotted, the system zaps it with an operation to fix it. This whole process is run by specific protocols called quantum codes, like the famous Shor code.
Now, that all sounds fantastic on a whiteboard, but here's where reality bites, and it bites hard. Actually building this cure into physical hardware, well, that comes with its own massive set of challenges. Let's dig into the real-world hardware hurdles.
See, here's the catch-22. The very components you're using to try and fix errors are also noisy and imperfect themselves. The hardware has super strict limitations. You have a finite number of qubits to play with, and every single operation you add to check for errors adds more complexity and, you guessed it, more chances for new errors to creep in. It is a ridiculously tough engineering problem.
And this quote just perfectly captures the dilemma that quantum engineers live with every single day. They are in a constant, high-stakes balancing act. The overhead, which is just a fancy word for all the extra stuff you need for error correction, has to be weighed against the very real, very strict limits of the hardware you actually have.
And this chart, wow, it really visualizes that overhead we were just talking about. To create just one reliable, useful qubit, what scientists call a logical qubit, you might need 9, or even dozens, maybe even hundreds of physical qubits just to protect it. That's a huge cost, and it shows you why we can't just throw more and more error correction at the problem and call it a day. So this brings us right to the practical, real-world choices that have to be made. Let's put ourselves in the shoes of an engineer for a moment, someone whose job is to actually make one of these incredible systems work.
All right, here's the challenge, and this is straight from the industry playbook. You've got a real quantum processor, and you know it's noisy. Your job is to come up with an error correction plan that actually works, but you have to do it with the extremely limited resources you have on hand. So, what do you choose? This table basically lays out the brutal trade-offs. You could go with a simpler strategy like a bit flip code. It gives you a medium amount of protection for a medium cost in qubits.
But what if you need really, really powerful protection? Then you might look at something like the Shore code. Its error suppression power is high, but just look at that resource overhead. It is very high. You might not even have enough physical qubits on your chip to make it work. This is the exact kind of decision engineers are forced to make every day.
And what are they aiming for with all these tough choices? They're chasing this number. A fidelity, basically its accuracy, of over 99.9%. For any quantum calculation to be considered trustworthy, it has to be incredibly precise. And hitting that kind of reliability with today's noisy hardware, well, that's the grand challenge right there.
So, after looking at the incredible promise, the big problem, and all the practical challenges, what can we take away from all this? Let's quickly recap what we've learned about building a reliable quantum future.
So what are the big lessons here? Well, first, we've learned that all those elegant theories have to survive contact with messy, real-world hardware. We've seen that progress isn't going to be some single magic bullet. It's a continuous, careful balancing act between power and resources. It's also super clear that this problem is way too big for any one field. You need physicists, engineers, and computer scientists all working together. And maybe the most important takeaway of all is that the real goal isn't some unobtainable perfection. It's about building practical, fault-tolerant systems that are just good enough to go out and change the world. Which leaves us with this one last big thought. In a lot of ways, we have the blueprint. We understand the theory behind quantum error correction. We know what needs to be built. The really crucial question, the one that's going to define the next decade of computing, is this: is our hardware actually ready to build it?